Welcome back to Plane Time with Ben Coleman. This is a broadcast from the Florida Aviation Network, and today we're broadcasting live and in the clear from our studios in Orlando, Florida. I'm Ron Timmermans, one of the co-hosts with Florida Aviation Network, and I'm delighted that you've returned again to watch this program. We are midway through an interesting presentation on weather from Dr. George Bartuska, who has joined us once again as one of our guests. And it's easy to see why he's known as the Weather Guy. He's just full of all kinds of great information to help us learn how to be better users of weather information and apply it to our piloting skills. And if by chance our viewer today's includes some Boy Scouts that are looking for qualification for your Weather Merit Badge, this is the part of the presentation that you want to pay particular attention to, because Dr. Bartuska is going to send us through some introduction to meteorology. And for those of you who are pilots, this will also be good information for you to kind of reinforce the concepts that you already know or refresh those that you've once learned and have since forgotten and the like. So Dr. George Bartuska, thanks again for joining us and being back with us. Please lead us through the next part of the presentation, sir.
Okay, Ron, thank you. As Ron mentioned, I'm going to start an introduction to meteorology presentation today. We've had a request from the Boy Scouts to cover some of the information that's in the Boy Scout Merit Badge book or requirements that they have to do. And the first one I want to go over is they're required to build some kind of a weather instrument. Now, we're in Florida. The one that I recommend everybody have wherever they are is a psychrometer to measure the temperature, the humidity, and the dew point. The dew point is incredibly important. Now, for the first approximately 100 years of the operation of the United States Weather Bureau, now called the National Weather Service, this device, a Sling psychrometer, was used to measure the temperature, the humidity, and the dew point. It has two identical thermometers, one with a wick, a little sock over the end of it, and this, we wet this, and usually you take some dental floss and tie it off here and tie it off here so it can stay on there. Because eventually what you're going to do, and I'm going to take the wick off for a minute, is you're going to whirl this around, and I'll show you with this other one. That's the previous style. This style of Sling psychrometer I like better because it's in a case, it won't get broken. But we're going to sling it around because we're trying to get water to evaporate off that wick. Now, how does the water get on the wick? We're going to take a little source of water and we're going to put some on there. I'm going to let it go on the floor here. And on the end of this one, there is a reservoir that we can put some water in the reservoir. To capillary action will keep the wick wet. It's sucking up the water already. Okay, and this one is mercury, just like that other one. Now, the Centers for Disease Control has finally outlawed mercury for use in weather instruments and any kind of instrumentation. You won't see a medicinal mercury thermometer in a doctor's office anymore, and you can't buy weather instruments anywhere that have mercury in them. So they've switched to just red-colored alcohol. And I will hold this up here so you can hopefully see that that one is red and it has alcohol in it. But it works the exact same way. You get the wick wet and then you sling it. And question is, how long do you sling it? Well, periodically you'll stop and with this hand, hold the thermometers and look at them and see what the reading is. You want to do this until you get the lowest reading on the thermometer with the wick on it. You don't want to go like this because your hands near the bulb will elevate the temperature and you'll be measuring the temperature of you instead of the atmosphere. Now, making your own, this is a psychrometer that I actually made probably when I was about 10 years old, starting interest in weather. Any two thermometers, so to speak, will do. You cut them off. Used to be all shoestrings were hollow, so you could use a shoestring for a wick. A lot of the shoestrings today are no longer hollow, but you can order wicks online. Now, one last thing I want to mention. This is a differential measurement. You need two thermometers that to start out read the exact same temperature. So if you're going to do this, I would go into the hardware store or into the department store and lay out all the thermometers they have. Or if you're going to buy online, I would order 10 inexpensive thermometers online. And when you get them, lay them out and let them set for a day, and then go back and find the 2 or 3 that are reading the exact same temperature, and then send the rest back. That's going to give you the most accurate results for measuring the temperature, the humidity, and the dew point. Okay, now we're going to go into our introduction.
George, if I may interrupt you just
Yeah.
for a moment, the Sling psychrometer, I find this is fascinating. So it's not an electric device, is it? It's not even battery powered.
No, they do have battery-powered ones, though. And I should mention, most of these have been eliminated today by electrical sensors and electronics. But Bendix made a device called a Psychron that basically took this Wechsler unit type thing and put it in a battery-powered unit. And instrument shelters then had a fan on it. But here's the thing to remember. If you're going to use a fan, you want to pull the air across the psychrometer. If you blow air on the psychrometer, you're going to get the heat from compressing the air, and you're going to get the heat from the motor and the fan. So whatever you do, the ideal thing is to get a motor on the outside of the instrument shelter that's pulling the air past it, and then you're in good shape.
Rather than pushing the air past
Right,
it. Okay.
right.
And the whole reason for doing the 2 temperatures, one for on the wick that is moistened, and the other
Right.
one that's dry, is to determine the difference between the temperature and the dew point. Is that correct?
Well, the difference between the wet bulb and the dry bulb, and understand if it's 100% outside, if the relative humidity is 100%, the dew point and the temperature are going to be the same, because evaporation can't take place. But if it's only 50% relative humidity, there's going to be a lot of evaporation. The thermometers are going to read different. Now, this psychrometer comes with a little built-in calculator on the side, like a slide rule. And it's not totally accurate, but it's good enough for what we're doing amateur meteorology. But when I was younger, used to have to look at a table in a book. Today, you can get your cell phone, type in calculation of dew point from wet and dry bulb, and you can just put the numbers in that you get from the wet and dry bulb, and it'll give you the relative humidity and the dew point.
So what you built a few years ago when you were 10 years old
Yes.
is measuring the dew point temperature and the actual temperature. Is that correct?
Right. The dry bulb would be the actual temperature, and the wet bulb, the calculation from the wet bulb and the dry bulb will give you the humidity and the dew point.
Very good. So this makes for a really interesting experiment for Boy Scouts and others that are
Sure.
interested in weather and building something for their merit badge. It's fairly simple to do with getting 2 thermometers that read very accurately the exact same temperature, and then use that to build the experiment like you just showed.
Right. And if you're wondering why we'd want to know what the dew point is, in the last week or so here in Florida, we've had fog. Anytime the temperature and the ambient temperature and the dew point are within 5 degrees of each other, you have the potential for fog. If they're the same number, you're definitely going to have fog. And if I make it to that far in the presentation, you're going to see I'm going to give an example of that. The other reason is there's a calculation in the Airman's Manual of the dew point. The dew point subtracted from the temperature divided by 4.4 times 1,000 will give you the cloud base height for the clouds at that particular time, where they're going to be, or et cetera. So there's various reasons you want to know what the dew point is. The really integrated reason is to understand instability in the atmosphere and some things called a skew-T diagram. And we won't get there today, but maybe next time we're on the air, we'll go into that. Okay, good question. Now, here's our introduction to weather. Okay, first thing I want to make sure we understand what the difference is between weather and climate. Weather is the short term. Weather describes how the atmosphere is behaving right now, in an hour or tomorrow, etc. We use these terms. You've heard the term forecasting, but there's nowcasting, forecasting, and hindcasting. Nowcasting is what is the weather right now. As Americans, we spend $2 billion a year to provide basic weather instruments to measure the status of the environment and the atmosphere, and we launch balloons twice a day at all of our weather stations, and we have radar, and we have all that in there. Basically, hey, what's the weather right now? What's the nowcasting right now? And we're going to use that information to figure out what the weather is going to be to do a forecast. And then if we have some kind of crazy weather like happened last night in the Midwest, we can go back and look at the weather conditions that were, and we call that hindcasting to see what happened. But the weather is what's happening right now. The climate is an average, and right now the standard average is 30 years. It's a running time average of what the weather's been for a long period of time to kind of tell you what the average weather is going to be in a particular area of the country. We have been talking about climate change and global warming lately. Things are changing. It's getting warmer. But that's the climate versus the weather. And I'm waiting. There we go. Now, what's a meteorologist? This is actually a very good question. A meteorologist is a term often used to describe anyone who studies meteorology. Popularly, any weather reporter on television is often called a meteorologist, but this isn't always the case. Now, there's a lot of text on here, and I apologize, but this is kind of the important part. A meteorologist is an individual with a specialized education who uses scientific principles to explain, understand, observe, or forecast the Earth's atmospheric phenomena and/or how the atmosphere affects the Earth and life on the planet. This specialized education would be a bachelor's degree or higher in meteorology or atmospheric sciences. Understand that a BS in meteorology or atmospheric sciences is essentially a degree in physics applied to the atmosphere. It takes 4 years. You might be asking yourself, well, why do we have meteorology and why do we have atmospheric sciences? Well, in the 1970s, when we started calling the people on TV meteorologists, the people who were all real meteorologists didn't like that because they had gone to college and studied this for 4 years. So a lot of places have changed the degree to be called atmospheric science. Now let me continue and I'll come back to that. Individuals who have little formal education in atmospheric sciences or who have taken only industry survey courses and who disseminate weather information and forecasts prepared by others are properly designated weathercasters. The broadcast meteorologists we watch on the news who explain weather and communicate weather forecasts are typically a mix of meteorologists and weathercasters. So the people we see doing the news at night may or may not have a degree in meteorology. They may have a degree in communications, which is good, and then they go on and get some weather training to be able to communicate the weather. Understand the role of the National Weather Service is to collect weather information and disseminate it to the media, and if there's a need for a weather warning, if there are going to be severe thunderstorms, tornadoes, or hurricanes, they issue that warning. Thus, every local meteorology office, every local National Weather Service office has the warning meteorologist in it and a chief meteorologist. But remember what I just said, a degree in meteorology or atmospheric sciences is a degree in physics applied to the atmosphere. And people that study science and physics and engineering like I did, we don't tend to be really good presenters without a lot of work. But people who study communications can be a lot better at communicating what we need to know. So it's a mix. In Florida, because of hurricanes, most of our people doing the weather on TV have degrees in meteorology, either from Florida State, Penn State, or Oklahoma State, various places around the country. We want to clarify that because that's, once again, part of the merit badge for Boy Scouts. So we have broadcast meteorologists who are doing the weather on the news. We have the National Weather Service meteorologists who work for the government. We have research meteorologists who study hurricanes, tornadoes, thunderstorms, specific things. We have teachers and professors, which is kind of where I fall right now. We have forensic meteorologists who investigate claims that involve things that happen due to bad weather. We have consulting meteorologists. I mentioned their specific, in our last presentation, I mentioned their specific weather information available to balloonists, to soaring glider pilots, to skydivers, to hang gliders. There are people who have services online where you can get forecasts just from them. And then we have the people who do nothing but climate meteorologists. And of course, they deal with classifying climates around the world and studying climate change.
George, if I may ask,
yes.
Are there some commercial airlines that employ meteorologists as well, and what are they called?
Oh yes. Most of the airlines have their own weather service, and those in general are all degreed meteorologists. And many of them have master's degrees and doctorates where they specialize in aviation weather. But it has changed because the National Weather Service has its own aviation weather system, and pilots are carrying around with them on their iPads all that information that's available.
So some of our young women and men that are in Boy Scouts and looking for careers eventually in their life, they could consider meteorology and any one of those things to include working for the airlines as a meteorologist.
Exactly. There's only one thing to remember. If you want to work for the National Weather Service, you have to have a degree that includes calculus. There are a lot of online services right now that are offering degrees in operational meteorology that don't include calculus. Well, that's okay, but you won't be able to be hired by the National Weather Service.
Okay.
Good. Okay, now, the military has its own group of weather people. I was in the Navy. The Navy calls them aerographers' mates. In the Air Force, they're called weather specialists. The Coast Guard employs individuals that do a bunch of things. They do weather, they do environmental science, they do a number of things, and the Army has their own section too. One of the things that happened back in the 90s is all the branches of service had their own weather schools, and somebody in the Pentagon said, you know what? Why don't we just have one weather school? It'll save money, we can concentrate it. So they're all in Biloxi, Mississippi now, is where everybody goes to get their weather training. Okay, now, the source of weather on Earth. And let me start off by saying, if the Earth didn't have an atmosphere, the Earth would look just like the moon. We would be full of craters, which we probably were to start out with until the atmosphere formed. Number two, where does the energy for the weather come from? It comes from the sun. Now, understand our sun is just another star, and it's not a very big star at that. But to give you an idea of the size, our sun is 109 times the diameter of the Earth. You'd have to put 109 Earths next to each other to equal the diameter of the Earth. One way to remember that number is former President John F. Kennedy was on PT Boat 109 during World War II. 109. But even more dramatic, the sun may be 93 million miles away, but it is 1.25 million times the volume of the Earth. In other words, if the sun was a sphere, hollow sphere, we could put 1.25 million Earths inside the sun. It's huge. It illuminates the Earth with 126 horsepower per second, and yet Earth only receives 1/2 billionth of the sun's solar energy output. In physics, we have three sources of energy. We have point sources, we have line sources, and we have plane sources. A point source is like a light bulb or the sun, where the energy is going out in all directions simultaneously. A line source would be like a fluorescent bulb or a line of traffic on a highway. They're giving out sound energy. And then a plane source would be a flat plane moving back and forth, like the window in your house when it retransmits acoustic noise. Okay, now, so that's the sun. What's the sun do? It is the reason we have heat and pressure and wind and moisture. The sun heats the oceans and the lakes and causes the water to evaporate. It takes energy to convert water into water vapor. When it gets up to a high enough level, it cools and the water condenses out and we get rain or clouds and precipitation. This water cycle, or the hydrologic cycle, is all a function of being heated by the sun. Now, I'm going to skip ahead a slide here. Greenhouse. We use this term greenhouse. The Earth's atmosphere acts as a greenhouse. If you've grown up in the southern United States, or if you're somewhere in the world where there is never any snow, this idea of a greenhouse may not make a lot of sense to you. I grew up in Indiana where it looks just like that in the winter. But if you have a greenhouse, you can grow plants and it can be 90 degrees inside that greenhouse as long as the sun is shining. Well, I'm backing up here, and that's how this greenhouse works. Well, that's exactly what happens on Earth. The weather, the atmosphere, is heated from the ground up. Most of the electromagnetic radiation that comes from the sun Most of it goes right through the atmosphere. Some of it is reflected back into space, but it goes through the atmosphere and it heats up the ground. It doesn't heat up the air very well because it's at the wrong wavelength. But when it heats up the ground, it's re-radiated into the atmosphere, and that's what heats the air. So we are living on a greenhouse. And it's a real good thing that we are, because the equatorial areas of the Earth get a lot more sunshine than the North and South Pole. And if we didn't have this greenhouse effect, there'd be incredibly hot places on Earth and incredibly cold places on Earth, neither of which would support human life. Now, how complicated can all this be? I mean, why do we have so much trouble doing a weather forecast? Well, your typical meteorology books start out with this picture. Imagine for a minute, instead of the sun being a point source, imagine the sun was a tube going around the Earth like a round fluorescent bulb. Well, as we see in the picture, what would happen in that situation is the air would be heated at the equator, and it would rise and go to the North or the South Pole, and as it did, it would cool, and then it would sink back down, and we would have these cells, and the weather would be easy to forecast. And those were called Hadley cells by a gentleman named Hadley back in the 1800s, because he thought he really understood what was going on. But Earth isn't that simple. Earth is tilted at 23.5 degrees, and it's rotating, and it has these weird looking things called continents that are really weird shapes. And when you combine that with the fact that the solar radiation is not uniform, it's unevenly heating the planet. It's much more spread out away from the equator. It's more direct at the equator. So it makes the thermodynamics of the Earth a very difficult thing to predict. Then we have in the lower picture what changes our seasons. Some people on TV every now and then, when they go in the audience on the talk shows, they'll ask people in the audience, they'll say, when do you think winter takes place? Is it when the sun is closer to the Earth or when the sun is further from the Earth, given that all planets orbit in an elliptical orbit? And most people will say, well, of course, it's when the sun is closer to the Earth, it would be summer, and when the sun is farther away from the Earth, it would be winter. But it turns out it has nothing to do with that, because we're talking about electromagnetic radiation going through space. The seasons are a function of the fact that the Earth is tilted 23.5 degrees, and it stays tilted as it revolves around the sun, and that's what gives us the seasons. Our winter has nothing to do with how close the sun is. Our winter has to do with the fact that we're tilted, in the northern hemisphere anyway. Our winter is when we're tilted away from the sun, and the southern hemisphere is in summer. And then in the summer, we're tilted towards the sun, and the southern hemisphere is tilted away from the sun. There we go. And so the end result is they're still heating at the equator, but because the Earth is tilted and because the Earth is turning, we experience something known as the Coriolis Effect, which means that the wind gets turned to the right in the northern hemisphere and it gets turned to the left in the southern hemisphere. And what the picture we see up there is a very simplified version of what we end up with are three cells in the northern hemisphere: the Hadley, the Ferrel, and the Arctic cell, and then we have the same three cells in the southern hemisphere.
So George, on this picture,
yes.
So we're looking at the Earth, and I see the arrows in the northern hemisphere that the wind turns towards the left, and the southern hemisphere
correct.
And so the Earth in this case is rotating from the left side of the screen towards the right side of the screen. Is that correct?
The Earth is turning counterclockwise. It's moving this way,
right?
From left to right. Yes.
Okay, good. So if I were looking down from the top, it'd be rotating counterclockwise. Okay, good.
Right.
So that kind of makes sense that the wind moves in that direction normally.
Right, and it's complicated by these factors, and this Coriolis effect is a very difficult thing to understand. Maybe in the next lecture I'll go into it. It gives everybody trouble, but it's a factor that affects weather, it affects flight, affects navigation at sea, it affects a lot of things.
If I may ask, George, why is it when I'm flying in my airplane, I almost always get a headwind no matter what direction I'm flying?
You're lucky.
Oh, okay. Continue, please.
It's right. Well, and in textbooks, there's a generic picture that shows most storms go from west to east. And so most people think, well, the wind can only go one direction. But if that were true, why do airports usually have several crossing runways?
Intersecting runways.
Because high and low pressure centers can vary the wind direction. Now, just a brief mention about the atmosphere. Our atmosphere is layered. The lowermost part of the atmosphere is the troposphere. It's about 7 miles high. And what's unique about the troposphere is normally the temperature goes down as you go up in altitude. A rule of thumb is at 30,000 feet, the temperature is 60 degrees below zero or less. But if we have an inversion in the atmosphere, that can be different, but we're not going to go into that at this time. Okay, now the next major source of weather are what we call air masses. And this was all discovered in the 1915 through World War I and just after World War I. The Norwegian School of Meteorology in Norway figured this out, and other people, that this occurs. We have pockets of air around the world, but I'm talking just the United States right now. We have these blobs of air that take on a certain characteristic based on where they're coming from. The two that affect us the most are the continental polar air and the maritime tropical air that comes off the Gulf of Mexico. The Gulf of Mexico area is very moist with a lot of water vapor in it, and the Canadian air is very dry and tends to be cooler or colder. It is the mixing of those two air masses that causes Tornado Alley and really severe weather. We get thunderstorms every afternoon in the summer of Florida, but they don't have that really dry Canadian air mixing with the maritime tropical air. It's more maritime continental mixing with maritime tropical. I only have a couple minutes left here. Air masses, as a result, those air masses coming together, we get fronts, we get cold fronts, we get warm fronts. A cold front shown at the top, basically the cold air is thicker, denser, pushes the cold air up, pushes the warm air up, and we get thunderstorms. In the case of and the frontal boundary, the boundary of those two air masses can be about 50 miles wide, and cold fronts can move 30 to 50 miles an hour. But below we have what happens when warm air encounters cold air. We get a warm front, and because the warm air is less dense, it rides up over the cold air, and that frontal boundary can be up to 300 miles wide. And because we're running out of time, I think I'm going to stop there, but I want to go forward and just talk about something. I got 1 minute left about Florida. The average rainfall in Central Florida is around 52 inches a year. Easy to remember because there's 52 weeks in a year, 52 cards in a deck of cards, and I average 52 tornadoes in Florida. But if we look at this overall rainfall map of the United States, the 52 inches is the light green there in Florida, but up in the upper left-hand corner, we see that where Mr. Bill Gates lives in Seattle, they can get 180 inches of rain a year. How is that? Because they have constant weather systems coming in off the Pacific Ocean, but they may only hear thunder 4 or 5 times a year. In Florida, we have thunderstorms every afternoon in the summer. We have at least 100 thunderstorm days a year. So that's a good place to wrap this up for now. Next time when I come back, we're going to talk about what more we can do with that dew point and relative humidity and the other aspects of atmospheric science.
It's a never-ending quest to learn about the weather. I'm sure you're a continued student of the weather as well.
Oh, yeah.
But thank you so much for sharing with us today. I'd like us to show us that 10-year-old project that you did with the psychometer. How do you say it again?
Psychrometer.
Psychrometer. Thank you. I couldn't tongue-tied today.
That's a homemade one.
Yep.
And here's one that you can buy. And I didn't mention, brand new, these Sling psychrometers can cost around $100, but you can buy them on eBay used for between $20 and $50. You just got to watch the website a lot.
So for the scouts that are looking for a project to build for their Weather Merit Badge, then this could be it for you, or maybe you'll figure out something else. But I'm so glad that you joined us today with the weather guy, Dr. George Bartuska, to learn some more about the weather. So we're out of time for today, but thank you very much for joining us today. This has been the Florida Aviation Network broadcast, Plain Time with Ben Coleman. Ben is not with us today. And oh, by the way, Ben, since you're not here, you and I are co-hosts for this normally, but since you're not here today, I am the main host. I just wanted you to know that, Ben. It's kind of an inside joke among the crew here. So I hope you will join us again in January 22 of 2022. We'll have two guests, Gary Dalkey with the Civil Air Patrol and Dean Brown, who is an air traffic controller in Indiana. It's going to be a great presentation. Ben will be back then and hosting along with me, and I'll look forward to seeing you then. Until then, I'm Ron Timmermans, one of the many hosts for the Florida Aviation Network. Thank you for joining us today. Please come back again.